Hello everyone, and thanks for listening to me today. I am excited to walk you through an interesting war story from the world of computing and engineering, specifically in the world of graph traversal. In this story, we will see the problems that can come when using inefficient algorithms for solutions like the traveling salesman. Let's not wait any further and continue to the story. A while ago, I got a mysterious tip about a tiny company that tested printed circuit boards. Out of pure curiosity, I drove to their building. It was nothing special on the outside, just another industrial box. Inside, though, I met the president and the leader engineer who has a surprisingly big problem. They showed me their machine, a robot with two probing arms. Each circuit board has groups of points called NATs that must be all electrically connected. To test a NAT, one arm stays still on the reference point, while the other arm runs around touching all the other NATs. If the probe completes a circuit, the points are connected. It sounds simple enough, until I watched it again. Everything looked fine, but one thing bothered me. The right arm was constantly racing across the board, while the left arm just sat there, practically bored. I asked how they chose the route for the right arm. Then they told me, easy. We start the points from the left to the right and visit them in that order. I couldn't help but laugh, because right then I realized something. They were accidentally trying to solve the traveling salesman problem, one of the most famous optimization challenges in computer science. I explained that their arm was basically a salesman visiting cities, in this case the net points, trying to find the fastest route. From left to right wasn't going to cut it. They nodded. This could help, but they had a bigger issue. And they asked me, can we bury the nets? The president leaned back and said, sorting is fine, but the real issue is that the big nets make the robot travel way too far. Isn't there some way to break these huge nets into smaller ones? That question changed everything, because suddenly, this wasn't just a traveling salesman problem anymore. It was a graph problem. If you think about a net as a set of points that all must be connected somehow, the simplest way to see their structure is through a minimum spanning tree, or an MST for short. An MST connects all points with the smallest set of wires possible. Here's the clever part. If you cut the longest edge, you get small clusters that still remain connected through shared points. Testing each small cluster ensures the entire large net is validated. Suddenly, that wandering robot arm didn't need to cross the whole board anymore. I was about to assign distances using regular geometry when I stopped myself, and I asked them, does moving diagonally take longer than moving straight? They told me no. The motors handle horizontal and vertical motion independently. That meant that the robot didn't care about Euclidean distance. It cared about something called the L to infinity metric, the maximum of horizontal or vertical movement. If the robot moved 1 inch up and 1 inch right at the same time, it only cost as much as time as moving 1 inch in one direction. That little detail changed everything. So we modeled a true robot movement cost, acceleration and deceleration, the proper distance metric, an MST for clustering, a TSP for each cluster. They coded it up, skeptical but curious. A few weeks later, they contacted me. Their testing robot now traveled about 30% less distance. For a machine worth 200,000 Rand, reducing wear and testing time was a huge win. This whole adventure taught and reminded me of something important. Real-world problems are often secretly graph problems in disguise. If you model the world correctly using minimum spanning trees, traveling salesman problems heuristics, and the right distance metrics, you can get enormous improvement with elegant, well-known algorithms. Thanks for joining us for the Nothing But Nets war story. We hope it gave you some insight into how theory meets practice and sometimes collides with it. And then, until next time, keep exploring, keep learning, and keep problem solving. Goodbye.